Here all today's lecture number 24. Here we will be going to design a problem of RCC column, and the type of column will be square type of column. Now first of all let us go through the statement. What is the problem statement? So we have to design a column which is having a height of 3.2 meter and end conditions are mentioned, which is effectively held in position and restrained against rotation at bottom end, and effectively restrained against rotation but not held in position at top. And this column is subjected to an axial load of 1600 kN under dead end live load condition, and we can assume moderate environmental conditions. So that means column is going to be constructed at a place where moderate type of environment is there. So that means column will be subjected to moderate type of environment. So exposure condition is given. Based on that, we can easily, going through IS 456, can decide what should be the minimum grade of concrete as well as what should be the steel. Now in step number 1, as usual, what we do, we select the grade of concrete as well as grade of steel, and as given in the statement, unsupported height of the column or unsupported length of the column is given 3.2 meters. Now what are the end conditions? At the bottom end, it is clearly mentioned that it is effectively held in position and restrained against rotation. So we can say that bottom end is fixed type of support, fixed type of end, which is not able to displace from the position, as well as it is restrained against the rotation. So that means movement at that end will not be equal to 0. So that's why it is a condition where complete restraint is given. Now when we are talking about the top end, so top end, it is given that it is effectively restrained against rotation but not held in position. So these are the two conditions which are already mentioned in the statement itself, which will be helpful for selecting the effective length of the column. Now since the column is supposed to be having moderate environmental exposure, so we can decide that grade of concrete which we can use, it is M25, and grade of steel as usual, it is Fe 450. And based on the environmental conditions, we can decide that a nominal cover for reinforcement, that minimum we have taken, that is 40 millimeters. Now in step number 2, where we are going to determine the size of column based on the loading conditions. So in the statement itself is clearly mentioned that axial load on the column is 1600 kilonewton, and based on the partial safety factor, we can easily calculate factored load, that is PU, that is 1.5 into 1600. So you can work out it is 2400 kilonewton, for which we are going to design the column and selecting the dimensions or the size of the column. Now here, since nothing is available regarding, or no information is available regarding what should be the area of the steel which we have to design. So initially, without any information or without any data available, we can assume a particular value, any value of area of steel, which should be as per the conditions mentioned in IS 456. That means it should be more than the minimum area of steel which we can provide, as well as it should be lesser than the maximum area of steel which is recommended in IS 456. So here what we can do, we let us assume the area of longitudinal steel, that is ASC, as 2% of the gross sectional area, so which is greater than 0.8% as well as lesser than 6%. So that means here we can work out that area of a steel under compression, that is 0.02 of a gross area of a section. So now what is the gross area of a section of the column? That is area of the concrete plus area of the steel. So from here we can rearrange the statement, rearrange this equation, that area of concrete will be gross area of a section minus area of steel which we have to provide. So here, since we are providing ASC is equal to 0.02 Ag, so we can easily calculate that it will be area of concrete will be 1 minus 0.02 into Ag. So that means we have to provide at least this much area of concrete, which is equal to 0.98%, 0.98 only 0.98 of area of a cross section. So using the earlier equation which we have discussed in the lecture number 23, that means you can use this equation. Pg is equal to 0.4 FCK AC plus 0.67 Fy ASC. And since we have calculated this Pg is equal to 2400 kilonewton, so we can put the data here in this equation. That is 2400 into 10 raised to power 3. It will become Newton. And 0.4 into FCK, since we have taken grade of concrete is equal to M25, so we can take 25. And the area of concrete, as we have just create here that calculation, that is 0.98 Ag and plus 0.67, and Fy is 415, and ASC is from this equation you can take, that is 0.02 Ag. And after solving this equation, we are able to get that this much area of this gross area is required. That comes out to be 156240 millimeter square. So we have decided that we will be providing or taking a square size of the column. So we can easily work out what should be the minimum size required. So after taking the square root of this value, we are getting the size of column is equal to 395 millimeter. So let us adopt a square column with the size 400 millimeter. So based on this, we can work out that gross area provided is 160,000 millimeter square, so which is greater than this required. So we can say this section with this dimension we can proceed with the numerical. Now we have to decide whether it is a short column, whether it is a long column. So in reference to IS codal provision which we have discussed in the previous lecture, that means we can refer table number 28 of IS 456, and based on that, if you go through the condition, so this is the extract from the IS 456, that means effectively held in position, and restrained against rotation at one end, and other end restrained against rotation but not held in position. This was the condition which was mentioned in the statement itself. So this will be the condition which will be looking like this. And for this type of condition, we have the formula. That means we can work out L effective is equal to 1.2 into L. L is the unsupported length of the column. So putting the value here, we are able to get that effective length of the column comes out to be 3.84 meters. And then we have to work out the slenderness ratio, because we have to decide or check whether it is a short column or whether it is a long column. And based on the formula given, that L effective by least lateral dimension. Now you can easily see that we have decided that it will be a square type of column having 400 millimeter size by 400 millimeters. So they both are the equal dimension. So least will be 400. So that's why we have put here the value. That means L effective is equal to 3.84 meter divided by 0.4 meter, the lateral dimension, least lateral dimension of the column. So after calculation, it comes out to be 9.6, and which is less than 12. So 12 was the condition for the short column. So that means it is very much clear here that based on the data available and based on the dimension which we have assumed, this column will be designed as a short column. So based on this, we have decided that we will be designing this column as a short type of a column. Now in step number 4, we have to apply the check, which is the code is mentioning that every column need to be designed for a minimum eccentricity. Now let us go through what are the conditions for the minimum eccentricity. So minimum eccentricity code is suggesting that it should be calculated by this formula, that is L by 500 plus B by 30. So L we have taken, that is unsupported length, that is 3200 divided by 500 plus 400 is the size of the column, and ultimately based on this equation it comes out to be 19.73. Now what code is giving the condition that this much eccentricity, this is the minimum eccentricity and should be less than 20 mm. So at least 20 mm. So it is less than 20 mm, and another condition is we have to check what will be the value of 0.05b. So it comes out to be 20 here. So we can, based on this condition, since the condition is fulfilled, that eccentricity, minimum eccentricity is less than 20, and we can use the formula for the calculation purpose, the short column capacity as suggested by IS 456-2000. You may remember that in the previous steps, we have already taken the same formula into consideration. Now it is verified that that formula is okay. We can proceed with the design problem. Now in step number 5, we are going to design what is the longitudinal reinforcement required, what should be the area of the steel, and how many number of bars we have to provide, what should be the diameter of the steel. So we can easily go through. Now in the previous step we have decided that we can use this formula which is mentioned in IS 456, and by putting all the information available, since we have decided that what should be the gross area of the section, so from this equation, by rearranging and by solving this equation, we can easily work out what is the area of steel which has to be taking compressive stresses and need to be provided. So based on the calculation, we came across the value that ASC required is 2984 millimeter square. Now we have to, first of all, we have to check whether this much area, if we provide that follow the conditions mentioned in the IS 456. So first condition was the minimum steel which we can provide or need to be provided, that is 0.8% of gross area of the section. So 0.8% of gross area of section comes out to be 1280 millimeter square. So that means we are providing 2984, which is greater than this, so it's okay. And second step is the maximum steel which we can provide, that is the limit restricted by the IS 456, that is 6% of gross area. So when we calculate 6% of gross area, that comes out to be 9600 millimeter square. So that means this area, if we provide this much area, then it will be following both the guidelines, both the condition. It is uh, greater than the minimum steel and lesser than the maximum steel, which is limited by the code. Now, since it is within the limit, we can recommend, as recommended by code IS 456, we can provide it. So here we have to decide what should be the size of the bar, that means diameter of the bar. So we have taken the 22 mm diameter bar, and we have provided 8 number of bars. So we have to provide steel as a symmetric type of section. So based on this, if we provide 8 number of bars of 22 mm dia at equal spacing, then ASC provided comes out to be 3042. So since this 3042 is again greater than 2984, which was required, so we can say this design here it is okay in this step. That means design of longitudinal reinforcement is okay. Now in step number 6, we are going to design transverse reinforcement. So we have decided that we will be providing lateral ties and to mount or to enclose the main reinforcement. Here you can refer this clause 26.5.3.2 part C, and the subpart is 2. Now here in a lecture earlier lecture we have taken that a minimum diameter of the steel bar which is required in case of a transverse reinforcement, we have taken as 16 millimeter because it is mentioned in the code, but it is mentioned wrongly, so it was 6 millimeter. So you can correct, and that means you can consider this correction in the earlier lecture as well as today's lecture. So how we have to decide the diameter of the transverse reinforcement? It shall not be lesser than what it will be going to calculate in step number 1 and 2. it should not be lesser than diameter of the longitudinal bar by 4. So diameter longitudinal bar we have decided 22 mm, so it comes out to be 5.5 millimeter. And the second, as I explained earlier, that it minimum should be 6 mm. So in code it was wrongly mentioned as 16 mm. So that correction we have to take care. So that means ultimately what we have to do, we have to provide the transverse reinforcement in the form of lateral ties, and having diameter greater than these two we can decide. So we have decided to adopt 8 mm dia bars lateral ties for the transverse reinforcement. Now we have to decide that what should be the pitch or center to center spacing between the lateral ties, and we have to follow the codal guidelines. Now what code is suggesting, code is giving some conditions, three number of conditions. Very first condition is least lateral dimension of the column, so it is a 400. So one condition is 400. Second condition is mentioned in code is should be 16 times diameter of the smallest. So we have a similar type of reinforcement that all the 8 bars are of 22 mm dia. So after calculation 16 times, that it gives 352 millimeter. And the third condition was 300 millimeter. So code is suggesting that what should be the minimum value that we have to take in consideration. So based on the above conditions, we have to decide that we will provide lateral ties 8 mm dia at 300 millimeter center to center pitch as a transverse reinforcement. So based on this condition, which even we have discussed in the previous lecture, you can go through that lecture also. So ultimately up to this point we are able to decide what should be the main steel, that means longitudinal steel, what should be the diameter, and how many number of reinforcement bars we have to provide, as well as the lateral tiles which we can provide, that is 8 mm dia, 300 mm center to center as a transverse reinforcement. Now last step is that we have to mention that reinforcement details we have to specify clearly. So first of all, whatever the dimensions we are taking in the drawing, the all dimensions are in millimeter, and main steel are 8 bars of 22 mm dia, and the lateral tiles are of 8 mm dia at a center to center spacing, which is called as pitch of the lateral ties, that is 300 millimeter center to center. Now what is the reinforcement detail of this square column? You can see clear here that these are the lateral ties, that is the black color bars you can see, and red color bars are the main reinforcement or longitudinal reinforcement. So we have provided the pitch of the lateral ties, that means center to center spacing between the lateral ties, that is a 300 millimeter. Now if you see here clearly, this is a square type of column, and we have arranged 8 number of bars. These are red color bars are the main reinforcement. So we have arranged these bars at equal spacing. So we can easily arrange 8 number of bars here. 400 mm was the size of the column, and this black color ring is actually the lateral tie, which you can see in this section also. And so we have to mention it clearly that these red color bars are 8 mm, 8 numbers, 22 mm dia. So when we are using hash here, it itself indicates that we are talking about the diameter of the bar, and 8 is the number of bars and 22 mm is the diameter of the longitudinal bars. And now here we have mentioned that a hash 8 we have written. So it means 8 mm dia rings or lateral ties at a center to center spacing of 300 millimeter center to center. So I recommend you, or I suggest you all, you take a different type of numericals and do practice for a square type of column as well as a rectangular type of column, different type of loading conditions. You can take different height of the column. So by bearing all these parameters or the data, you can do practice for a number of numericals. And if you find any doubt or any query in this lecture, in this numerical problem, you can comment on the YouTube, where we have loaded this lecture. You can ask, we will be able to, definitely we will be responding to your queries.